Logarithmic differentiation is a method of differentiation which is applicable or can be used if a function is a product, a quotient, power, or root of two or more differentiable functions of x. So again, if there is a product, a quotient, a power, or root of two or more differentiable functions of x. So we have the three steps here to follow to be able to perform logarithmic differentiation. So the first step, we take the natural logarithm of both sides of the equation. Next is use the loss of logarithm to simplify the right member of the resulting equation. And of course, the third, we differentiate and we solve for y prime. So for example, we want to find the derivative of the function y equals 2x plus 1 square root of 3x plus 5. So as you can see here, it's a product of 2x plus 1 and square root of 3x plus 5. So another method that we can use here is actually the product rule. But we can also use here logarithmic differentiation. So according to the steps, the first step to follow is to take the natural logarithm of both sides of the equation. So therefore, we write ln, the natural log of y, is equal to ln of 2x plus 1 square root of 3x plus 5. The second step is to simplify the right member of the resulting equation by making use of the properties of the loss of logarithm. And as you can see, we're multiplying here, so we can split it into two logarithms, which is a sum of those two logarithms. So we're going to write that as, that's now equal to, okay, that's ln y is equal to ln of 2x plus 1 plus the ln of the square root of 3x plus 5. And so we can now differentiate, or this ln right here, because we have 3x plus 5, and as you can know, square root of 3x plus 5 is equal to 3x plus 5 raised to the power of 1/2. And by the loss of logarithm, okay, let me just write that. This is equal to ln of 2x plus 1 plus, again, you can just, when you reach this part, you can start differentiating, but you can also get rid of the radical sign here by writing this as ln of 3x plus 5 raised to the power of 1/2. And by using the loss of logarithm, ln 2x plus 1, that exponent right there can be used or can be transferred as a coefficient right here, that's 1/2 ln of 3x plus 5. Then you can perform differentiation here. So it's really up to you. So differentiating, the derivative of ln y is 1 over u, so 1 over y, times du dx, or this is y prime, equals, that's 1 divided by 2x plus 1, multiply it to the derivative, that's 2, and then copy 1/2 right here, times 1 over 3x plus 5, multiply it to the derivative of 3x plus 5, which is 3. Alright, so this is now 2 divided by 2x plus 1 plus 3 divided by 2 times 3x plus 5. This is still 1 over y prime. And so y prime is equal to, multiplying both sides by y, that's y times 2 over 2x plus 1 plus 3 divided by 2 times 3x plus 5. And then we have to express y in terms of x. And from our given, y is equal to 2x plus 1 times the square root of 3x plus 5. So we're going to change this, 2x plus 1 square root of 3x plus 5. Alright, times 2 over 2x plus 1, or we can actually find the LCD right here. Okay, let's find the LCD, write it as a single fraction. So it's just basically the product of the denominators. Let's write the fraction bar, copy 2x plus 1, 3x plus 5. So this is 2 times 2, 3x plus 5 plus 3 times 2x plus 1. And then we can actually combine. Also, we can cancel 2x plus 1 right here. That can be cancelled. And we can combine the 3x plus 5's. So because the exponent in the denominator is greater, so we can leave that in the denominator later on. Okay, so simplifying right here, we have 4. 4 times 3, that's 12x. Multiplying this here, and then also here. So this is 4 times 3, that's 12x. And then 4 times 5, that's 20. Okay, plus 6x plus 3 divided by, okay, 2 square root of 3x plus 5. Again, because the degree of 3x plus 5 in the denominator in the previous line is 1, and the degree in the numerator is 1/2. So you can combine them. And so simplifying the numerator, that would be 18x plus 23 divided by 2 square root of 3x plus 5. That is our y prime. And that is by logarithmic differentiation. So this is another way you can always use product rule for that one. So just to show that we can use logarithmic differentiation if there is a product or quotient of two functions. Okay. Now, we can also use it if there's an exponent or power of two functions. For example, y equals x to the power of x. So take note that the exponent now is a variable, so we cannot use the power rule anymore. So we have to use logarithmic differentiation. So first, we have to take the ln of both sides. So ln of y equals ln of x to the power of x. And then using the formula, so x ln x equals ln of y. And so because we cannot split this anymore, because there's only a single ln, so it's now a product of x and ln x, so we are now going to use the product rule. So differentiating, again, that's 1 over y prime, equals x times the derivative of ln x, which is 1 over x, plus ln of x, and the derivative of x is equal to 1. So 1 over y prime, is actually equal to 1 plus ln of x. So isolate y prime is equal to y times 1 plus ln x, but then we have to express y again in terms of x, and y is equal to x to the power of x. 1 plus ln of x. And that is our derivative using logarithmic differentiation. So actually, by using that logarithmic differentiation, if there is already a variable in the base and in the exponent, we can simplify it to a formula. So the derivative with respect to x of u to the power of v. So if it's in this form, meaning the base has a variable, the exponent also has a variable, similar to this one. So the formula now would be, that would be equal to, you simply copy u to the power of v. As you can see, just like this, this is u to the power of v. And then you multiply it to the derivative with respect to x of v ln of u. So where is this v ln of u in our example? This is our v ln of u. So we solve for the derivative of v ln of u, which is this one. So that is our formula for logarithmic differentiation. So if we are going to use the formula to find the derivative of the given, so the derivative of y equals x to the power of x, then dy dx as a shortcut is equal to, you just copy x to the power of x and multiply it to the derivative of v ln u. What is our v? It's simply x, so x ln of x. And so that's x to the power of x times 1 over x plus ln x, which still leads us, because again, that's just derived from that previous solution, is equal to x to the power of x times 1 plus ln of x. Okay, this formula, u to the power of v times the derivative of v ln u. Okay, another example. We want to find the derivative of y equals sine of x to the power of x. And if we're going to use that formula right there, so dy dx is equal to, you just copy the given, sine of x to the power of x, and multiply it to the derivative with respect to x of v ln u. And v, remember, is the exponent. Our exponent is x, and our u is sine of x. ln rather. It's v ln u. So it's ln x ln of sine x. Okay, remember the formula right here. It's v ln of u. Okay, so differentiating, we now still copy sine of x to the power of x times, we can enclose that in a parenthesis because we're going to be using the product rule. So x times 1 over u, that's 1 over sine x, multiplied to the derivative of sine x, which is cosine x, plus copy ln of sine x times the derivative of x, which is equal to 1. So cosine x over sine x is actually cotangent x. So our derivative dy dx is just equal to sine x to the power of x times x cotangent x plus ln of sine x. And that's it. That's how we perform logarithmic differentiation. Okay, let's have another example. we want to find the derivative of y equals x plus 1 to the power of 2x. Okay, so dy dx. First, we copy x plus 1 to the power of 2x. Multiply it to the derivative with respect to x of v, which is 2x, ln of x plus 1. Okay, so let us change the parenthesis here with a bracket so we do not get confused. Okay, again the formula, it's u to the power of v, derivative with respect to x of v ln of u. Okay, so our v here is 2x, our u is x plus 1. Okay, again, so copy x plus 1 to the power of 2x, multiply it to the derivative, so copy 2x times 1 over x plus 1, and the derivative of x is 1, plus ln of x plus 1 times the derivative of 2x, which is 2. So remember that we cannot multiply x plus 1 to 2, only to ln of x plus 1. So let's simplify this. This is x plus 1 to the power of 2x. And then we're going to combine this. So x plus 1, this is now 2x plus 2 times x plus 1 ln of x plus 1. So simplifying further, our derivative dy dx using the loss of exponents, this is now equal to x plus 1 to the power of 2x minus 1, because they have the same base, so we just subtract the exponent. The exponent of x plus 1 in the denominator is 1. Okay, times 2x plus 2 times x plus 1. So we can actually factor out 2, so we can put 2 outside here. Okay, and then let's just remove 2 here. Okay, so x plus 1 ln of x plus 1. And so that is our answer. So we cannot combine these right here because we're multiplying x plus 1 to ln of x plus 1. So that is just our final answer. And for the last example, we want to find the derivative of y equals ln of x to the power of x. So the derivative dy dx is equal to, we want to copy ln of x to the power of x, and we are going to multiply it to the derivative of x ln of ln x. I hope you get that, because our formula again, dx of u to the power of v is equal to u to the power of v times the derivative of v ln of u. And so our v here is x, and our u is ln x. That's why we're taking the ln of our u, which is ln x. Okay, so to continue, that's ln x to the power of x. And we still use the product rule. So copy x. The derivative of ln of ln x is 1 over u. So 1 over ln of x. multiply it again to the derivative of ln x, which is 1 over x plus ln of x. So we can just cancel x right here. So that's ln of x to the power of x times 1 over ln of x plus the ln of ln x. So we can just again combine this, ln of x to the power of x times 1 plus ln of x times ln of x divided by ln of x. And so simplifying, our derivative dy dx is equal to the ln of x raised to the power of x minus 1, again because the exponent of ln x in the denominator is 1, and we multiply it to 1 plus ln x ln of x. Okay, so that is logarithmic differentiation.